Our final lesson in Topic 3 is 3.6, Theorems about roots of polynomials. The fundamental theorem of algebra states, given a polynomial in standard form with degree n, it will have up to n real solutions and exactly n complex solutions. What this means is if you have a polynomial, it can cross your x-axis up to the same number of times as the degree of the polynomial, but you'll always be able to find the exact amount of complex solutions that may or may not include those real x-intercepts. To create equations based on roots of polynomials, we're going to start off with understanding what roots could be formed. And we're going to begin with conjugate root theorems. Or theorem, it should just be one. There's only one theorem. The conjugate root theorem is similar to the complex conjugate that we used when we divided complex numbers earlier in Topic 3. If a complex number in the form a plus bi is a given root, then the form a minus bi would also be a root in the polynomial. This is important to know as we create polynomial equations with given roots. The example on the right has a whole lot of space for really no work at all. It says if 4 minus 3i is a root, and remember a root is the same as a 0, then the conjugate is also a root. And remember the conjugate just changes the sign in between the a and the bi. We would then say 4 plus 3i is also a root. So instead of having just one, we now know that there would be two. The next part isn't a theorem, but it's a way to create certain factors based on roots that are already given. The sum and product rule. It's used to create specifically a quadratic function or a quadratic factor. So it says sum and product. That means you'll need to know two roots and find their sum and their product. Sum is found simply by adding the two roots together, and that is going to represent the b coefficient in our quadratic function. The product of the two roots will represent the c value, or that c number in the quadratic function. This is the template that we use. This will work to create a quadratic function or factor when a equals 1. So notice I don't have another coefficient in front of x squared. And we read it as x squared, and it's always minus, and then depending on what the sum is, that may change. But then the template's always plus the product. I just wrote too big to fit that in there. So x squared minus the sum times x plus the product. Here's how easy this is to create a quadratic function or factor given two roots or zeros in a function. Example 2a. What is a quadratic function p with rational coefficients in standard form? All this means is that we're going to write it from biggest exponent down to smallest, and we're not going to have any, imaginary type coefficients in front of our variables. So it says such that p of x, so p of x equals is what our final answer will look like, has 6 and negative 13 as roots. What this means on the second part is that x would cross, or the function would cross the x-axis at 6 and at negative 13. So what we want to do is simply find their sum and product. B is going to represent the sum, that's 6 plus negative 13, and that equals negative 7. C, that constant, is their product. 6 times negative 13 would be negative 78. Once you know the sum and the product, we literally just follow the template. So taking that information, if we write it out as x squared minus bx plus c, oh, I forgot that p of x. So we're going to write p of x equals. We'll be official with our function notation. The x squared will never change. That stays the exact same. The definition is minus, but notice b is negative 7. So we'll have to adjust for that when we're done. Then it's plus, and c is negative 78. To simplify the work on the right, we'll write it as p of x equals x squared, and we'll change that double negative to plus 7x, And then plus negative 78 would be minus 78. If you were asked to factor that and find the zeros, you would get positive 6 and negative 13 as your final answer. All right, one more example. What is the quadratic function? Again, p with rational coefficients in standard form. And now p of x has 2 plus 5i as a root. This is an example of a complex root. 2 plus 5i, that's one root, but it's complex. So one complex root. In order to be quadratic, we need to know two roots. Since we're only given one, there's got to be something else that we can do with this information. Recognizing that this is complex, we're going to apply the complex conjugate rule. So the complex root rule, sorry, not complex conjugate, I said that from before. The complex root rule states if 2 plus 5i is a root, then 2 minus 5i also must be a root for this polynomial function, in this case a quadratic function. Now we have this root and this one. We have two roots, and that will help us determine a quadratic function. We're going to do the same thing we did up above. We're going to determine b and c. Oh, that's an equal sign. B and c. To get b, we're literally going to add the two roots together. 2 plus 5i plus 2 minus 5i. And here's something that will always happen when we decide to, or when we create a quadratic factor. The I terms always cancel out, and our sum becomes positive 4. The product will require a little bit more work. We'll have to multiply these two complex numbers together. Similar to how we multiplied by the complex conjugate when we did division earlier this topic, and when we're done, the i's should cancel out again. If we do first, 2 times 2 is 4. If we multiply the outsides together, 2 times negative 5i would be negative 10i. Multiply the insides, we would get positive 10i. Now be careful on that last product. Positive 5i times negative 5i would be negative 25, but then I squared. So positive 5 times negative 5 is negative 25, but I times I becomes I squared. To combine like terms, the two I parts in the middle, positive 10i and negative 10i, cancel out. I squared, how many of you remember what that equals? I squared is equal to negative 1. And what that will do is it makes that negative 25 actually become positive 25. So if I squared is negative 1, negative 25 times negative 1 would become positive 25. And 4 plus 25 would give us a constant of 29. Going back to our template to write our final answer, p of x equals x squared minus b times x plus c. In our case, we'll have p of x equals x squared minus 4x plus 29. And that would be our quadratic function, and to write higher ordered polynomials, that would be a quadratic factor. These are your notes for 3.6, Part 1.